In this lesson objective, we discussed buoyancy, but before we can talk about buoyancy, we have to recall a few key points from our lessons on hydrostatic pressure. Okay, so the first key point is that pressure is only a function of depth. It doesn't matter how far I move side to side or fore and aft within a fluid, pressure is only going to vary as I move up and down within that fluid. And from that understanding, we were able to derive an equation, a hydrostatic pressure equation, equation 2.13, which states that my pressure at point 2 is equal to my pressure at point 1 minus the density of the fluid times the acceleration due to gravity times the change in depth or the change in height within that fluid. The last key point to note before we move on is that if I have a body submerged in a fluid, in any fluid, then the pressure exerted by the fluid on that body acts inward and normal on all sides of the body. So let's talk about buoyancy force, and what I'm going to derive is going to be valid in any fluid and for any shape, but it's easier to imagine or to visualize or conceptualize if I imagine, let's say, a cube underwater. So let's draw our fluid surface, and let's say it's atmospheric pressure acting at the surface of that fluid. Let me put a coordinate axis at the bottom here that states that my vertical direction is z and my horizontal direction is y. And let's draw this cube. Now, I'm only drawing the cube in 2 dimensions. Imagine it goes into your screen to form a complete cube. And this cube has some density. Now let me label the corners so that we can use those for our resultant vectors later. And let's say that the top face, face AB, has a depth of z1, and the bottom face, DC, has a depth of z2. Now, again, because pressure is only a function of depth, that means the pressure as I move from A to B is going to be the same. So I have a uniform hydrostatic pressure distribution on face AB, and again it acts inwards on the body, so it's pushing down. And then on face DC, I have the same thing, except it's acting upwards because it acts towards the body, and it's uniformly distributed in obviously a greater value than the pressure that's distributed on face AB because it's at a greater depth. Now, on the sides, of course, I also have a pressure distribution, and this is I guess a ramp load, you could consider it. And you can see that it increases, the pressure increases as we get deeper and deeper on the sides. But you can see it's equal on face AD and BC. Now, you learned previously how to resolve those pressure distributions into resultant hydrostatic pressure forces. So I've done that, and you can see that I have forces on all 4 sides acting inward. And note that the forces on face AD and BC are not acting directly through the centroid. They're acting where the centroid of their force distribution would be that we could derive from their pressure distributions. And if I did the sum of the forces in the y direction, what I'd find is that my force acting on AD is equal and opposite to the force acting on BC. So they really cancel out, and they don't have any relevancy when we're discussing buoyancy. So let's just remove those just for clarity, but they do exist. Now, if I sum then the forces in the z direction, you can obviously see from the picture that they're not the same, but there is a difference between the two because of their differences in depth. And so that difference we define as the force of buoyancy. So recalling from hydrostatic pressure that hydrostatic pressure is the density of the fluid times the acceleration of gravity times the height or the depth at which it acts. I've replaced the force on face DC and the force on face AB with the hydrostatic pressure. And because force equals pressure times an area, I have to multiply it by the area. And because it's a cube, the area of the top face for AB and the area of the bottom face DC are the same, so I just put that on the outside of the parentheses. Now, what else is the same? Well, density is the same. It's the same fluid, and acceleration of gravity is a constant, so that's the same. So let's pull that outside the parentheses as well. And so with our new equation, or the same equation, just kind of rewritten, we can see that the buoyancy force equals the density of the fluid times the acceleration of gravity times that change in depth times the area of, let's say, the top face. Well, that area of the top face times that change in depth is what for a cube? And I'm hoping you're saying it out loud right now that that's the volume of the cube. And this is true for any shape. It's just obviously easier to compute and easier to see with a cube. So I can therefore say that my force of buoyancy is equal to the density of my fluid times the acceleration due to gravity times the volume of the body. And that's equation 2.42 in your textbook. Now, a key thing to note is that the volume of the body is the volume of the submerged portion of the body. So in our example, the entire body is submerged, so the volume is its entire volume. But if it were floating on the surface and only part of it was submerged in the water, then I would only use the volume of that submerged portion. An easier way to look at it, or another way to look at it, is that the volume of the body is the volume of water that's displaced by the body. So I'm only going to account for what's in the water, or in any fluid for that matter. So let's replace those resultant forces with the force of buoyancy. And I want you to note that the force of buoyancy acts upward and through the centroid of the submerged body. And that should make sense because there should be more pressure and therefore more force on the bottom side where we're deeper. So let's talk about Archimedes' principle. And Archimedes' principle has three facets, which I've really kind of discussed all of them, but let's list them out. The first of which is that the force of buoyancy equals the weight of the displaced fluid. So the weight of the volume of displaced fluid is equal to the force of buoyancy, and that makes sense. The next is that the force of buoyancy acts upward and through the centroid of the body, as I showed on the previous slide. And now, for three, there's three possibilities. The first of which is if my force of buoyancy is greater than the weight of the body. And if that's the case, then the body floats. And that's what we call positive buoyancy. Now, as you can imagine, the next possibility is that if the force of buoyancy is equal to the weight of the body. And if that's the case, and you've probably seen this before where something's been underwater, for example, and then just kind of hangs out at that level. Or think of a hot air balloon that you heat up the air to a point where it maintains a certain altitude and then stays there, just kind of hangs there. That's when the body is suspended in the fluid. That's when the buoyancy force and the weight of the body are the same. That's called neutral buoyancy. Now, obviously, the last possibility is that if the force of buoyancy is less than the weight of the body, then as you can imagine, the body sinks. And that's what we call negative buoyancy. Now, this is easiest seen by doing an example problem. So I'm going to do example problem 5.2. And if you don't have example problem 5.2, or if it's changed by the time you're watching this video, the problem statement is here, and you can pause the video in order to read the complete problem. But I'm going to move on and do the analysis. So let's use our problem-solving process, and we'll start off with our known. So Alvin, our little submarine, our little submersible, achieves neutral buoyancy at 1,000 feet. So really it should state that we want to achieve neutral buoyancy at that depth. So what do I need to find? I need to find the volume of the water that must be blown from the negative tank, and I want that in feet cubed. Now the negative tank, if you have a submersible or a submarine, they have to take on water in these negative tanks that makes their weight or their greater than the buoyancy force by increasing their density, their mass per unit volume, and it causes them to dive. And then when they reach a depth that they want, they release the water out of the tank, they expel the water using pressurized air out of the submarine, therefore reducing their density or reducing their overall weight, and that if that's equal to the force of buoyancy, then they are neutrally buoyant, and that's where they stay. So let's do the diagram and data below. So I'm going to draw my water, and I'm going to say it's atmospheric acting at the surface. And the problem stated that I can model Alvin, my submersible, as a cylinder. So let's put that cylinder underwater, and it's at a depth of 1,000 feet. And the cylinder that we're modeling Alvin as has a diameter of 6 feet and a length of 18 feet. Now, inside it's taken on some water in these ballasts, and so we're just going to draw that on there just for a visual. And this overall body, and because it's a cylinder, which is a simple body, and we're going to assume it's the same material throughout, has a center of gravity, and that center of gravity happens to correspond with the centroid in this case, because it's a homogeneous simple shape. And it has weight force acting down through the centroid. And I've labeled that weight nu because when I'm drawing this picture, I'm drawing it when it's at neutral buoyancy, which means it's the new weight. It's the weight it started at minus the weight of the water I've expelled, and that new weight is where it's neutrally buoyant. So I'm going to draw my picture at the state I'm trying to analyze. And therefore there's a force of buoyancy that's acting upward through the centroid on the body that's equal to that new weight. And let's list the rest of the numbers that were given to us. Our density of water is 62.3 pounds mass per foot cubed. The temperature of the water is 50 degrees Fahrenheit. And my original weight, the weight I started at when I had taken on water in order to initiate my dive, was 32,000 pounds of force. So let's make some assumptions. Well, the first assumption is water is incompressible, and that's a very valid assumption. Water doesn't get compressible until very, very, very deep. If we're talking 4,000 meters below the surface of the water, it's still change in volume is still only about 1.8%. So incompressible, especially at 1,000 feet, very valid assumption. Alvin is not moving. Obviously, that's one of the equations we have, or one of the assumptions rather, we have to use in order to use our equations, because these are hydrostatic equations. So obviously, we have to be static. And then we're going to assume that the water can be expelled instantaneously. So I can model this moment in time. Now, you could gradually lose the water as you would gradually apply brakes to your car, but we're going to assume it's all expelled instantly. I'm looking at a snapshot in time where I've just said this is the volume of water I need to expel. Boom, it's done. Now I'm neutrally buoyant. So I put that drawing on the top right hand side for my analysis so we can refer to it if we need to. And so let's start with what we know. Go with what you know. I know that Alvin is neutrally buoyant, and if Alvin's neutrally buoyant, then its buoyancy force and the new weight have to be equal, right? So if I start off with that fact, I can then work my way through the problem. So recall the fact that the force of buoyancy is the density of the fluid times the acceleration due to gravity times the volume of the body that's submerged. And that's equation 2.42 that we showed earlier. So therefore, I can say that the force of buoyancy, I can replace that with the density of my water times acceleration due to gravity times the volume of my submersible is equal to my new weight. Now, I stated previously, but let's write it down, my new weight is my initial weight, the weight I started off my dive with, minus the water I had to expel out of my ballast tanks in order to achieve neutral buoyancy. And since it's a cylinder, the volume of my body can easily be computed with the dimensions I was given. It's obviously the area of a circle, so the cross-sectional area that the cylinder, pi 4d squared, diameter squared, times the overall length. So let's mash this all together, and let's say that my density of my water times acceleration due to gravity times the volume of my body equals my initial weight minus the weight of the water I expelled. So I've simply just replaced the term weight new with initial minus water out. And now let's rearrange that, because what we want to solve for is the water that we had to expel out, the weight of the water that we had to expel. And so I just rearrange the equation to say that my initial weight minus the buoyancy force is equal to the weight of my water out. Now, the density of my water is given. Gravity is a constant. Volume I can compute. I showed you the equation up a couple lines. And my initial weight was given. So I have everything I need to determine the weight of the water I need to expel in order to achieve neutral buoyancy, in order to make my weight equal to my force of buoyancy. So let's solve for that. So I've simply plugged in my numbers here, 32,000 pounds of force for my initial weight. My density is 62.3 pounds mass per foot cubed. And notice in green, I had to convert those units. I had to convert pounds mass to slugs because I want my overall units to be pounds force. And so a pound force is a slug times a foot per second squared. So I have to convert out by dividing by 32.174 pounds mass in order to cancel out those pounds mass and get slugs feet per second squared. And then for my foot cubed term, obviously since I'm multiplying it by the volume, those feet cubed will cancel out. And that gives me the weight of my water out. And my weight of my water out I find to be 293 pounds of force. Well, the problem asks for the volume of water I have to expel. So what are we going to do? Well, recall the fact that force equals mass times acceleration, Newton's second law. So weight equals mass times acceleration due to gravity. Well, I don't know the mass of the fluid. I know the density of the fluid, which is mass per unit volume. So if I say my density times my acceleration due to gravity times my volume, that's equal to the weight. So again, I know what the weight of the water is. I know what the density of the water is. I know what the acceleration due to gravity is. And I can solve for the volume. So let's rearrange my equation in terms of what I know. And I've run out of room here, so let's continue over to the side. And if I put in my values, again, note the conversion. I had to cancel out those pounds mass from density because I'm multiplying it by acceleration due to gravity in feet per second squared, and I want those pounds force to cancel out, and I want volume there in the denominator to come to the numerator to give us our volume. And what we get is that the volume of water I have to expel out is 4.703 cubic feet. And double underline answer, there you have it. So hopefully this cleared some things up about buoyancy, and you'll be able to solve more problems in the future on your own.